All right, let's jump right in. Welcome to the Explainer. Today, we are unlocking the secrets behind what is, honestly, one of the most reliable, structural, and frankly, heroic shapes in all of mathematics. We're talking about the isosceles triangle. We're going to break down its unique properties into some really clear, highly digestible pieces.
Here's a quick roadmap for today's explainer. We'll start with the triangle family tree, then meet the isosceles triangle, dive into its specific theorems, check out similarity and proportionality, calculate perimeter and area, and wrap it all up with how the isosceles shows up in the real world.
But, before we even touch the pure math, just think about this for a second. Look up at the roof of a house or stare at the trusses of a massive steel bridge. Why is this specific two equal-sided shape always staring right back at you? Well, it's definitely not an accident of design. It's actually the ultimate mathematical problem solver for stability and balance. I want you to keep that real-world image in the back of your mind as we unpack exactly how its mechanics work.
Okay, section 1. Meet the isosceles triangle. So the word isosceles itself, it isn't just some arbitrary mathematical jargon thrown together. It actually derives straight from two ancient Greek words. You've got isos, which means equal, and skelos, which means legs. Equal legs. So by definition, an isosceles triangle is literally any triangle that has two sides, or legs, of the exact same measure. If you can lock those two Greek roots into your memory right now, I promise you will never forget the core property of this shape.
Moving on to section 2, the triangle family tree. Think of triangles as a kind of spectrum. On one far end, you have the equilateral triangle. That's total uniformity, all three sides and angles perfectly equal. Then, way over on the other end is the scalene, completely asymmetrical, zero equal sides. But sitting right there in the sweet spot is our isosceles. It boasts exactly two equal sides and two equal base angles. This gives it a unique, beautiful kind of dual symmetry that makes it incredibly stable but also super adaptable, unlike the rigid equilateral or the chaotic scalene. Oh, and interestingly enough, an isosceles triangle can actually overlap with a right triangle containing exactly one 90-degree angle. And because it's so adaptable, this superhero shape has three major variations depending on its internal angles. First up, you have the acute isosceles, where both base angles are sharp, measuring less than 90 degrees. Second, there's the right isosceles, where that top vertex angle is a perfect 90-degree corner. And third, the obtuse isosceles, where one angle stretches out wider than 90 degrees but stays under 180. The cool thing is, no matter how much you stretch or compress that top angle, as long as those two skeles, those two legs, remain equal, it totally retains its isosceles superpowers.
Which brings us to section 3, the isosceles triangle theorems. This right here is the absolute foundation of everything we're discussing today, the isosceles triangle theorem. It basically states that if two sides of a triangle are congruent, meaning they are completely equal in length, then the angles directly opposite to those sides are inherently congruent, or equal too. Think of it like a perfectly balanced scale, or maybe a mirror reflecting itself. You simply cannot have equal sides without the angles pushing against them being perfectly equal as well. They are forever mathematically linked.
Now, in geometry, we don't just take things on faith, right? We prove them. And the proof for this is incredibly elegant. Step 1. You draw a median line straight down from the top point, perfectly bisecting the base in half at exactly 90 degrees. Step 2. Just observe that our one big triangle has suddenly become two smaller right-angled triangles sitting side by side. Step 3. Because they share that middle line, they have equal bases and equal outer legs, we can use the SSS, side-side-side, or SAS, side-angle-side congruence rules to prove these two halves are identical twins. And finally, Step 4. Because the two halves are identical, those two outer base angles must logically be identical too. That middle median acts as a flawless mirror line. And what's truly beautiful about this math is that it's a two-way street. The main theorem tells us equal sides guarantee equal opposite angles. But then the converse theorem simply flips the script. If you have a triangle and you notice two equal angles, you are mathematically guaranteed that the sides opposite to them are equal. The logic is absolutely flawless and functions perfectly in both directions, which makes it a super reliable tool when you're trying to solve complex geometry puzzles. Okay, let's look at section 4, similarity and proportionality rules. So when you're comparing shapes, you might wonder if they're essentially the same thing, just maybe scaled up or scaled down. To prove if two triangles are proportional twins, we use 4 punchy criteria. SSS for side-side-side, AAA for angle-angle-angle, AA for just angle, and SAS for side, angle, side. If you apply these tests to two isosceles triangles and they pass, well, you know for sure their corresponding sides are perfectly proportional, even if one is the size of a postage stamp and the other is the size of the Great Pyramid.
And speaking of proportions, we have the basic proportionality theorem. This dictates that if you draw a line inside a triangle that's totally parallel to one of its sides, and it intersects the other two sides, it's going to divide those two sides in the exact same ratio. So imagine slicing the top off an isosceles triangle with a perfectly parallel line. That smaller triangle left at the tip, it is in perfect mathematical harmony and proportion with the original larger shape.
All right, Section 5, calculating perimeter and area. Finding the perimeter, the total distance around the outside, is remarkably straightforward. P equals 2A plus B. Because we already know two of the sides are identical, we don't need to add three different numbers together. We just take A, which represents our hero's equal legs, multiply it by 2, and add B, the base. It's a highly efficient little shortcut born directly from the shape's definition. Now, finding the area actually gives us two pretty powerful options. The classic formula is area equals 1/2 times base times height. Very standard, very easy, assuming you know the height. But what if you only know the lengths of the outside walls? Well, that is exactly where Heron's formula comes in. Area equals 1/4 times the base multiplied by the square root of 4a squared minus b squared. Okay, I know it looks a little intimidating at first glance, but it's really a phenomenal alternative tool that lets you calculate the area using literally nothing but the side lengths.
Finally, Section 6, isosceles in the real world.
Because let's be real, the numbers and proofs we just covered are the invisible forces holding up our physical world. In architecture, the roofs over our heads use isosceles trusses because that dual symmetry evenly distributes the heavy load of the roof right down to the walls. In engineering, ramps and massive suspension bridges rely on this exact shape for rigid stability against wind and weight. In art and design, it gives us these incredibly pleasing structured patterns. And in physics, the entire study of optics and light reflection relies on the precise, predictable angles of isosceles geometry. It literally is a superhero keeping our world stable. So we've covered the origins, the proofs, the formulas, and the highly practical applications of this incredible shape. With your new geometry vision fully activated, I want to leave you with this question. Where will you spot an isosceles triangle saving the day next? Seriously, the next time you walk over a bridge or just look up at a ceiling, you are going to know exactly the mathematical magic working behind the scenes. Keep your eyes open and keep learning.